Okay, so here we are. We've covered a few things on matrices so far. And in particular, we've talked about a few operations that you can perform on matrices. You can add two matrices if they have the same size. You can subtract them if they have the same size. And you can also multiply a matrix by a scalar. So that kind of naturally leads to the question, is it possible to multiply two matrices together? And yes, we're going to work up to a definition of that. Now, my approach to teaching matrix multiplication is a little bit different from the books. I cover all the same things, but I'm going to do it in sort of a different order. And my reasoning for that is that matrix multiplication is a notoriously tricky thing for students to wrap their minds around. Not because the process is difficult. It's not necessarily difficult. It's more that the definition of matrix multiplication, the procedure for it, seems to have no relevance. It seems like a very random thing to do to two matrices, and it doesn't really speak to its usefulness until you've done a lot more with that concept. So I'm going to approach this in a way that's a little bit more it helps us get to the relevance of matrix multiplication just a little bit quicker. So with that, let's talk about matrix vector products. This is a specific case of the more general matrix multiplication. Let's suppose we have a matrix A, it's an m by n matrix, and X is going to be an n by 1 column vector. Okay, it's the same n here as here. So in other words, the number of columns in this matrix is going to be the same as the number of rows in this matrix. Otherwise, this is not going to work. Okay? What do I mean when I talk about multiplying A to X, or the product AX? What does that mean? Well, what I do is I define it this way. This looks very messy. This is actually an m by 1 column vector, though. Even though this looks like a big matrix, notice this is a11 times x1 plus a12 times x2 plus blah, 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 all the way until I get to the very last product, a1n times xn. If you look at where these came from, a11 times x1, first row, first column entry times the first row entry here, a12 times x2, and so on and so forth until I get to this last one. That's why I need the same number of columns here as rows here. That guarantees that I have a one-to-one correspondence between these entries so that I can match them all in this way. But multiplying all of those and then summing the results gives me a single scalar so that this row only contains one number, whatever I get from doing this operation. Okay. Then I go on to the next row and I do the same thing. And you can think of this as taking this column vector and kind of picking it up, turning it 90 degrees, and dropping it on a row of A. Whichever numbers land on the entries of A, those get multiplied, and then you sum all the results. So I'm going to drop this column on the first row, do the multiplication, and then the adding, that gives me that entry. Drop this column on the next row, that gives me this, and then so on and so forth until I've done that to all the rows of A. Okay? That's a weird way to think about that, but there's a way of making better sense of that using what we talked about in the preliminary videos that I made. So this operation looks like the result of a dot product. In fact, it looks like I took the dot product of this vector, this column vector, with this row vector to get this first row right here. And then the dot product of this column vector with this second row right here. And so we can actually represent this much more concisely. If A has R1 through Rm as its row vectors, so this is R1, R2, and so on and so forth. Rather than write this big mess, I can just think of AX as this, R1 dot X, R2 dot X, all the way through Rm dot X. Each of these rows is just a dot product of a row with this single column vector. Okay? So that's a much nicer notation. Now, this is the reason why I introduced dot products all the way in that preliminaries set of videos. It's because your book actually doesn't talk about dot products until you get to chapter 3. But this notation is incredibly useful for understanding matrix multiplication. So let's do an example. I want to evaluate the product of this matrix with this column vector right here. Okay. Now, notice the, well, actually, let's just go ahead and do the process, and then I'll mention what I was thinking about in a moment. So this is a 4x2 matrix. 4 rows, 2 columns, and I'm multiplying by a 2x1 column vector. And what we do is we imagine picking this column vector up, dropping it on this first row, and then multiplying whatever lands on what. So 2 times 3, 2 times 3, plus 5 times -1. That would be what I get for my first entry up here. Then I do it again. I drop this column on this row, 2 times 0, plus 5 times 2. Then I do it again. Drop this column on this row, 2 times 4, plus 5 times 5, and then drop this column on the last row, 2 times 0, plus 5 times -3. I didn't leave myself quite enough space, but that's all right. Okay, let's wrap this up. 2 times 3 is 6, plus -5, that would be 1. Then I'm going to have 0 plus 10 here, that's 10. 8 plus 25, what's that? That's 33. And then 0 plus -15, so I got -15. Okay, now one thing I want to point out about this is the dimensions. Here, I multiplied an m by n matrix. Actually, let's not call it m by n. Let's be specific. It's 4 rows. It's a 4x2 matrix. 4 rows, 2 columns. And I multiplied that to a 2x1 matrix. Remember, we said that the number of columns in this matrix needs to match the number of rows in this matrix. Or in other words, if I write the dimensions this way, whoop, that was off the screen the whole time. That's what I was referring to before. These inner dimensions here have to match, 2 and 2. But look at the result. We ended up with a 4x1 column vector. Where did the 4 and the 1 come from? Here and here. So those remaining dimensions here, the number of rows in the first matrix, number of columns in the second matrix, indicate what my result is going to look like, what the dimensions of that resulting matrix is going to look like. Okay, and right now we're only dealing with vectors on this side, but that same idea is going to carry over to the more general case of matrix multiplication. So we'll see that again soon. All right, let's keep going with this. So why am I talking about matrix vector multiplication, a matrix times a vector? Well, right away, defining matrix vector notation or multiplication this way gives us a way of representing systems of linear equations using matrix multiplication. Suppose you have this system of linear equations. It's a system of m equations in n variables. Okay, now we know that we can create an augmented matrix out of this thing, but I don't want to approach it that way. Instead, what I want to do is start by just looking at the coefficients, a11, a12, all of the a's, and taking all of those coefficients and putting them into a matrix by themselves. This almost looks like an augmented matrix, but if it were an augmented matrix, it would have an extra column for the b's, and that's not showing up here. So it's not an augmented matrix. And then the variables, the x1, x2, all the way through xn, I'm going to load those into a column vector. x1, x2, and so on, right? And then the constants, b1, b2, all the way through bm, is going to be another column vector, an m by 1 column vector. I can take this linear system and represent it this way. And you'll notice that the ax here, if we go through the steps that we just did for multiplying a matrix to a column vector, it's the dot product of that column vector with each row of this matrix, and that's exactly what the left-hand side of each of these equations looks like. So that gives us a very natural connection between matrix vector multiplication and each of these linear equations. I can set that equal to the vector b, which would indicate that the result, remember, an m by n matrix times an n by 1 matrix should be an m by 1 matrix, which this is also an m by 1 matrix, and all of these corresponding entries of the matrix AX should be equal to the corresponding entries of B if it's going to represent the system of linear equations. So this AX equals B is an extremely concise and compact way of representing a system of linear equations. And it has a huge number of benefits that we're going to see throughout chapter 1, which is that we're going to develop a lot of properties of matrices. And if we recognize a system of linear equations in matrix form like this, we call this the matrix form for a system of linear equations, then we can apply properties of matrices toward solving systems of linear equations. It opens up all of these doors, thinking of it in this way. Okay? Now, we have this other useful way of thinking about matrix vector notation, which is different from how we're thinking about it here. So it's another application of this. And in fact, it's an incredibly, incredibly important one. So for this, let's think of these column vectors as vectors in Rn or Rm, right? What does multiplying a vector in Rn by the matrix A do? It produces a vector in Rm. So in this sense, we can kind of think of this as a function. Remember in the preliminaries section, we defined this notation for functions. Instead of calling it f, I'm going to call it Ta. A is going to be an m by n matrix, and so that A is showing up here as a subscript. And we can think of, we're going to define Ta of x in this way. It's equal to Ax. This looks simple, but it might be confusing what it is we're even talking about here. Well, notice this is function notation, and the x is bold here. That implies that it's a vector, not just a real number. This notation tells me that the inputs, the domain of this function, is the set of ordered n tuples, Rn. So x is an ordered n tuple, or we can think of it as an n by 1 column vector. If I were to multiply A, my matrix, my n by n matrix, by x, my n by 1 column vector, the result is going to be an m by 1 column vector, and we think of that as the output of this function. X is the input, Ax is the output, and that would live in Rm. Okay? This idea is central to linear algebra, and I'm just going to mention right here something that I'm going to do that your book does a little bit different. This is something that we call a linear transformation, and it turns out that pretty much all of linear algebra can be viewed through the lens of these things called linear transformations. I'm not asking you to know that terminology yet. At the end of chapter 1, I'm going to post a video. I'm sorry, at the end of chapter 3, not chapter 1, I'm going to post a video that's going to introduce linear transformations of this type and use it to unite all of the ideas that we talk about in chapters 1 through 3, because those ideas might seem very disconnected. But if we think of things through the lens of linear transformations, we can see all sorts of connections between this algebraic stuff and the geometric stuff that we deal with in chapter 3. Okay, so I want you to remember this. But let's talk about, or let's just do an example. So A, I'm going to let that be the 2 by 3 matrix given here. And we want to evaluate T of A, or TA of this column vector, -3, 4, 5. So notice first of all, this is a 2 by 3 matrix. According to this notation, you don't need to write this in finding the solution, but this is just for practice. The domain of this function should be Rn, where n is the number of columns. In other words, R3. And we can see that we are taking a vector from R3 and plugging it into this function. The end result should be a vector in R2, which should correspond to the number of rows of this matrix. So what is TA of -3, 4, 5? Well, by definition, it's the matrix A, 1, 0, 1, 2, 1, 0, times the column vector, -3, 4, 5. Okay? The result should be a 2 by 1 column vector. It should belong to R2. And I get that by taking the dot product of this column with this row, and then the dot product of this column with that row. -3 times 1, 5 times 1, that's negative 3 plus 5, or 2. Notice I skipped 4 times 0 since I know that that's going to be 0. It's not worth spending mental energy on that. Negative 3 times 2 is negative 6. 4 times 1 is positive 4. Add those and I get negative 2. Okay? So even though this just looks like a normal matrix multiplication problem, I'm thinking of this vector as my input, and I'm thinking of this vector as my output. So that this matrix multiplication is really being thought of in the perspective of a function. It's like a function. Okay? All right. Now let's get to the more general definition of matrix multiplication. So this time, I want to be able to multiply a matrix times another matrix that's not necessarily a column vector. We're going to let A be an m by n matrix, and B is going to be an n by p matrix. And as I kind of showed before, we need the number of columns of the first matrix to be the same as the number of rows of the second matrix. The outer dimensions, the rows in A, number of rows in A, and the number of columns in B aren't going to matter. This needs to match this, however. So I'm going to notate the columns of, the rows of A, R1 through Rm, we have m of them, and the columns of B are going to be C1 through Cp. The product of A times B is evaluated by taking dot products of rows in A with columns of B. So for example, if I want the 1, 1 entry of the product AB, I dot the row 1 of A with column 1 of B, R1 dot C1. If I want the 2, 1 entry of AB, I dot the second row of A with the first column of B, and so on and so forth. Okay, so you can see the subscripts would match the position of these entries in this matrix. This is not how your book defines matrix multiplication. They use a more messy notation for it. And again, that's just because they don't introduce dot products until chapter 3. In fact, in your book, once you get to the point where they introduce dot products in that section, they say, hey, we can think of matrix multiplication this way. I like it better introducing this now. Okay, so let's practice this with a product of two matrices. I want to do A times B, where A is this 4 by 2 matrix, B is this 2 by 2 matrix. Okay, 5, 2, 0, 1, negative 2, 3, negative 1, 0, times 3, 1, negative 2, 8. Okay? Now, let's think about what the dimensions of my result are going to be for a moment. We have a 4 by 2 matrix, 4 by 2, and we're multiplying that by a 2 by 2 matrix. We need these inner dimensions to match, and the reason for that is because the number of rows in this matrix will determine the number of entries in each column. 2 entries in each column. The number of columns in this matrix will determine the number of entries in each row. 2 entries in each row. If I'm going to do a dot product of each column here with each row here, I need the number of entries in each to match. 2 here, 2 here. Okay? The end result is going to be a 4 by 2 matrix. So it's actually going to have the same dimensions as this guy. All right. Now to save on space and time, I'm going to talk through these dot products instead of writing a bunch of arithmetic out. I need to dot this first column with this first row, which is what this is saying, R1 dot C1. So that's 5 times 2, that's 15. 5 times 3, that's 15. 2 times negative 2 is negative 4. Adding those gives me 11. Okay. In fact, I'm going to work through this first column before I move on to the second column. So I'm going to keep using this first column on each of these rows. 3 times 0, negative 2 times 1, that's negative 2. 3 times negative 2, and then negative 2 times 3, that's negative 6 plus negative 6, or negative 12. 3 times negative 1, negative 3. Notice I just ignored the 0 there. Now move on to the second column of this matrix. 1, 8 times 5, 2. So that's going to be 5 plus 16, 21. 1, times 0, 8 times 1, that's 8. 1 times negative 2 is negative 2. 8 times 3 is 24, so that should be 22. And then 1 times negative 1 should be negative 1. Again, ignore the 0 because it contributes nothing. There's my answer, and it is a 4 by 2 matrix. Notice. Okay? You don't need to write the dimensions below each matrix like I'm doing here. I'm just doing it to illustrate the connection. Okay? So what we're going to do, and I'm going to do this actually in the next video, is talk about some other ways of thinking about matrix multiplication, some other ways of representing these products and things like that, stuff that's going to be useful for us later on when we use matrix multiplication for different applications.